There's a number that haunts cosmology: 13.8 billion years. We say it confidently, as if we've measured the entire lifespan of existence itself. That question isn't just philosophical anymore. It's become one of the most urgent puzzles in modern physics. Let's start with what we actually know. And I mean truly know, backed by evidence so solid that scientists across the globe agree on it. The universe is expanding, not just drifting apart, but actively stretching like a balloon being inflated. Galaxies aren't flying through space away from each other. Space itself is growing between them. This discovery came from Edwin Hubble in 1929. He pointed his telescope at distant galaxies and noticed something strange. Their light was shifted toward the red end of the spectrum, not because they were red, but because they were moving away from us. The faster they moved, the more their light stretched. It was like listening to an ambulance siren as it drives away, the pitch dropping as distance increases. But Hubble realized something profound. If everything is moving apart now, then at some point in the past, everything must have been closer together. Wind the clock back far enough, and you arrive at a moment when all the matter and energy in the universe occupied an impossibly small space. That moment became known as the Big Bang. Except it wasn't really a bang at all. There was no explosion in space. Space itself began expanding. Time itself started ticking. Before that moment, the concepts of before and after didn't exist because time hadn't been invented yet. This is where human intuition starts breaking down. We're used to thinking of time as a river that's always been flowing. But what if the river has a source? What if you could trace it back to the exact spot where the first drop of water emerged from the ground? The evidence for this cosmic origin story is overwhelming. We can actually see the afterglow of creation itself. In 1964, two scientists named Arno Penzias and Robert Wilson were testing a radio antenna in New Jersey. They kept detecting this annoying background hiss no matter where they pointed their equipment. They even cleaned out bird droppings from the antenna, thinking that might be the source. It wasn't. What they discovered was the cosmic microwave background radiation, the oldest light in the universe, stretched and cooled over billions of years, but still detectable. It's like the heat signature left over from a fire that burned 13.8 billion years ago. This radiation comes from every direction in space, a faint whisper from when the universe was only 380,000 years old. But here's where the mystery deepens. That radiation tells us what the universe was like after it had already begun. It's a baby photo, not a conception photo. It shows us the universe when it had cooled enough to become transparent to light. Before that moment, the cosmos was so hot and dense that photons couldn't travel freely. They were constantly scattered by charged particles, making the universe opaque like a thick fog. So we have this wall, a cosmic horizon beyond which we cannot directly see. Everything before that moment is hidden from us, not by distance, but by the physics of light itself. This is when scientists started asking the dangerous question. If we can't see past that wall, how do we know what happened before it? How do we know the Big Bang was truly the beginning? The mathematics of general relativity, Einstein's masterpiece describing gravity and space-time, suggests that if you rewind the expansion far enough, you reach a point called a singularity, a moment of infinite density and infinite temperature, where all the laws of physics break down. The equations literally produce infinities, which is physics code for "we have no idea what's actually happening here." Infinities in physics are usually red flags. They're signs that your theory has been pushed beyond its breaking point. It's like trying to use a map of your city to navigate across an ocean. The map works great for what it was designed for, but it becomes useless when you ask it to do something it wasn't built to handle. This is exactly what happens when we try to apply general relativity to the earliest moments of the universe. Einstein's theory describes how matter and energy curve space-time, creating what we experience as gravity. It works brilliantly for explaining planets orbiting stars, light bending around galaxies, even the orbit of Mercury down to incredible precision. But at the singularity, at that moment of infinite density, general relativity encounters quantum mechanics. And these two theories don't play well together. Quantum mechanics governs the realm of the incredibly small. Atoms, particles, the fundamental building blocks of matter. It describes a world where particles can exist in multiple states simultaneously, where the act of observation changes what you're observing, where uncertainty isn't just a limitation of measurement, but a fundamental feature of reality. General relativity, on the other hand, describes the realm of the incredibly large, stars, galaxies, the curvature of space-time itself. It's deterministic, smooth, continuous. It assumes you can measure things with arbitrary precision if you have good enough instruments. These two frameworks have been tested to extraordinary accuracy in their respective domains, but they use completely different mathematical languages. They make contradictory assumptions about how reality works. And when you try to combine them to describe what happens when an entire universe is compressed into a space smaller than an atom, the math explodes into nonsense. This is the problem of quantum gravity. We don't have a theory that successfully merges quantum mechanics with general relativity. We have candidates, string theory being the most famous, but none have been experimentally verified. Without quantum gravity, we can't describe what actually happened at the moment of the Big Bang. But some physicists have started wondering if we're asking the wrong question entirely. What if the Big Bang wasn't the beginning? What if it was a transition, a bounce, a phase change in something that already existed? There's a theory called loop quantum cosmology that takes this idea seriously. Instead of a singularity, it proposes that the universe underwent a quantum bounce. Imagine the universe contracting under its own gravity, getting smaller and denser, heading toward what looks like a singularity. But before it reaches that point of infinite density, quantum effects kick in. They create a repulsive force that reverses the collapse, causing the universe to bounce back into an expansion. In this model, our Big Bang was actually a big bounce. There was a previous universe before ours. It had its own history, its own galaxies, possibly its own laws of physics. Then it contracted, bounced, and became our universe. The singularity never actually happened because quantum mechanics smoothed it out. This isn't just speculation. The mathematics of loop quantum gravity, when applied to cosmology, naturally produces this bouncing behavior. The equations don't allow infinite density. They build in a maximum compression, a point where quantum effects become so strong they overwhelm gravity's pull. But this raises an immediate question. If our universe came from a previous universe, where did that universe come from? Are we just pushing the problem back one step? Maybe. Or maybe the universe is eternal, bouncing forever between expansion and contraction. Each cycle could last trillions of years. Each bounce could reset the clock, scrambling information from the previous cycle so thoroughly that we can't detect traces of what came before. There's another possibility that sounds even stranger. What if our universe emerged from nothing at all? Not from empty space, but from an actual absence of space, time, matter, and energy. From true nothingness. This idea comes from quantum mechanics, specifically from something called quantum tunneling. In the quantum world, particles can do things that are forbidden by classical physics. They can appear on the other side of barriers without actually crossing them. They can borrow energy from the vacuum, use it briefly, and pay it back before the universe notices. Some physicists, like Alexander Vilenkin, have proposed that the universe could have tunneled into existence from nothing. In quantum mechanics, even nothing has structure. The vacuum isn't empty. It's filled with quantum fields that fluctuate randomly, creating virtual particles that pop in and out of existence. These fluctuations are normally tiny, lasting for unimaginably brief moments. But Vilenkin's equations suggest that occasionally, rarely, a fluctuation could be large enough and last long enough to create not just a particle, but an entire universe. Our universe could be one such quantum accident, a random fluctuation that grew into everything we see around us. This sounds like getting something from nothing, violating conservation of energy. But there's a loophole. The total energy of the universe might actually be zero. All the positive energy locked up in matter and radiation could be exactly balanced by the negative energy of gravity. If the books balance, if the universe costs nothing energetically, then quantum mechanics might allow it to appear spontaneously. But even this explanation requires something to exist beforehand. The quantum fields, the laws of quantum mechanics, the structure that allows fluctuations to happen. You can't have quantum tunneling without quantum mechanics. So we're still left with the question of where those underlying laws came from. Unless, of course, the laws of physics aren't fundamental. What if they're emergent properties of something even deeper? What if asking where the laws came from is like asking where the rules of chess came from? They're not physical things that need a physical origin. They're just patterns, relationships, structures that describe how things behave. This leads to some philosophers suggesting that maybe the universe doesn't need a cause at all. Maybe existence is simply a brute fact. The universe exists because it exists, and demanding an explanation for that is like demanding an explanation for why 1 + 1 = 2. Some things might just be true without requiring deeper justification, but physicists aren't comfortable with brute facts. The entire project of science is based on the idea that everything has an explanation, that if you dig deep enough, you'll find causes and mechanisms. Throwing up your hands and saying it just is feels like giving up. So the search continues. Particle physicists build larger accelerators, trying to recreate the conditions of the early universe in laboratory collisions. Cosmologists launch satellites to study the cosmic microwave background with ever greater precision, looking for subtle patterns that might reveal what happened before the observable universe began. Theoretical physicists fill blackboards with equations, seeking the elusive theory of quantum gravity that might finally let us peer past the singularity. Each approach has discovered remarkable things. We now know the universe is 13.8 billion years old to within 1% accuracy. We know what it's made of, roughly 5% normal matter, 27% dark matter, and 68% dark energy. We can trace cosmic history back to when the universe was less than 1 second old, describing in detail how particles formed, how the first atomic nuclei came together, how the cosmic microwave background was created. But that last fraction of a second remains stubbornly mysterious. The first trillionth of a trillionth of a trillionth of a second after the Big Bang is where our theories break down, where quantum effects dominated everything, where space-time itself was probably doing things we can't yet describe mathematically. This is the Planck epoch, named after Max Planck, who first realized that nature has fundamental scales built into it. Below a certain size, about 10 to the minus 35 meters, our usual concepts of distance stop making sense. Before a certain time, about 10 to the minus 43 seconds, our usual concept of time stops working. These aren't just technical limitations. They represent actual boundaries in how the universe operates at its most fundamental level. Beyond those boundaries, we're truly in unknown territory, and beyond the Big Bang itself. That question might not even be properly formed. Asking what came before time began could be like asking what's north of the North Pole. The question uses concepts that only make sense within a framework that didn't exist yet. But here's what makes this puzzle so captivating. We're not just asking about ancient history. We're asking about the nature of existence itself. Every answer we consider opens up new questions about why there's something rather than nothing, about whether the universe had to exist, or if it's just one possibility among infinite others, about whether consciousness like ours was inevitable or an impossible accident. These questions have driven human curiosity for thousands of years. Ancient philosophers wondered about first causes and prime movers. Medieval theologians debated the nature of creation and eternity. Now we have mathematical equations and satellite observations to guide us, but the fundamental mystery remains as deep as ever. The most honest answer to what came before the Big Bang might be that we don't know yet. But that yet is important. Because unlike previous generations, we have tools that might actually help us figure it out. We have theories that make testable predictions. We have observations that constrain what's possible. We're narrowing down the options, ruling out ideas that don't match what we see. And what we're discovering is that the question itself might be more subtle than we thought. Time might not be fundamental. Causality might work differently at quantum scales. The universe might not have a single origin, but could be part of an eternal structure that never began. These theories aren't just mathematical games. They're attempts to describe something real, something that might have actually happened. And the strangest part, some of them suggest the Big Bang wasn't even special. Consider eternal inflation. According to this idea, our Big Bang was just one bubble forming in an infinite sea of space-time that's been inflating forever. Imagine a pot of boiling water where bubbles constantly form and expand. Each bubble is a universe with its own Big Bang, its own laws of physics, its own story. Our universe, just one bubble among countless others, each beginning with what looks like a Big Bang from the inside, but is really just a local event in something much larger. This solves several puzzles. It explains why the universe appears so uniform in every direction. Different regions had time to equilibrate before our bubble formed. It explains why certain physical constants seem finely tuned for life. If there are infinite bubbles with different constants, we naturally find ourselves in one, where the numbers allow observers to exist. But it also means the Big Bang wasn't the beginning of everything, just the beginning of our cosmic neighborhood. Then there's the cyclic universe model. Picture the cosmos as breathing, expanding, and contracting in an eternal rhythm. Our Big Bang was the moment of maximum contraction before the current expansion phase. Before that, another universe, older and perhaps completely different, that collapsed down to nearly nothing before bouncing back. This bounce, driven by quantum effects that become important at extreme densities, replaces the singularity with a transition point. Loop quantum gravity calculations support this idea. When you apply quantum mechanics to space-time itself, the math shows that matter can't collapse to infinite density. There's a repulsive force that kicks in at incredibly small scales, preventing the singularity and causing a bounce instead. If this is right, we could theoretically see evidence of the previous universe encoded in the cosmic microwave background, like a message in a bottle from before time began. But here's where it gets really strange. Some physicists think time itself might not be fundamental. Carlo Rovelli and others have developed theories where time emerges from more basic quantum relationships. At the deepest level, there is no time, no before and after, just a web of quantum events connected by probability. What we experience as the flow of time is like temperature emerging from molecular motion, something that only makes sense at large scales but disappears when you zoom in far enough. If time is emergent, then asking what came before the Big Bang is asking the wrong question. It's like asking what happened before there was such a thing as before. The universe doesn't have a timeline with a starting point. It's more like a complete geometric structure that simply exists, and our experience of flowing through it is a feature of how our consciousness works, not a feature of reality itself. This connects to the block universe idea from relativity. Einstein's equations treat time as just another dimension, no different from space. Past, present, and future all exist equally. Nothing is actually flowing or becoming. What we call now is just where we happen to be located in the four-dimensional structure of space-time, like a specific spot on a map. The Big Bang is then not an event that happened in the past, but a boundary of the space-time structure, like the edge of a table. These aren't just philosophical musings. They make different predictions about what we might observe. The Penrose conformal cyclic cosmology, for instance, predicts circular patterns in the cosmic microwave background from gravitational waves produced in the previous cosmic cycle. Some researchers claim to have found these patterns. Others dispute the findings. The debate continues, but the key point is, we're looking. We're testing ideas about what preceded the Big Bang with actual observations. String theory offers yet another perspective. In this framework, our universe might be one of countless brains, higher dimensional objects floating in an even higher dimensional space. The Big Bang could have been the result of two brains colliding. Before the collision, both brains existed separately, perhaps for eternity, perhaps as part of their own cycle of collisions and separations. This ekpyrotic scenario explains some features of our universe that inflation struggles with. It naturally produces a nearly flat universe with small density variations, exactly what we observe. and it suggests that before our Big Bang, there was indeed something. Two universes on a collision course. But all of these models face a deeper problem. They push the question back, but don't eliminate it. If there's eternal inflation, what started the inflation? If the universe is cyclic, what set the cycle going? If brains are colliding, where did the brains come from? Every answer seems to require something that came before it, an infinite regress of prior causes. Unless there wasn't anything before, quantum mechanics offers a truly radical possibility. In the quantum world, particles can appear from nothing, borrowing energy from the vacuum for brief moments before disappearing again. The more energy borrowed, the shorter the particle can exist. But what if you borrowed an entire universe worth of energy? Alexander Vilenkin showed mathematically that a universe could tunnel into existence from literally nothing, not even empty space or quantum fields, but absolute nothingness. The universe as we know it, with all its space, time, matter, and energy, could be a quantum fluctuation that popped into existence without any prior cause. This sounds absurd. How can something come from nothing? But quantum mechanics is full of things that seem impossible, yet happen constantly. Particles tunnel through barriers they shouldn't be able to cross. Properties remain undefined until measured. The quantum world plays by different rules than our everyday experience. And here's the key insight. If the total energy of the universe is zero, then creating it doesn't violate any conservation laws. The positive energy in matter and motion is exactly balanced by the negative energy in gravitational fields. Add it all up and you get zero. Creating a universe costs nothing. No energy input required. It can just happen spontaneously, like a virtual particle, but one that never has to pay back the borrowed energy, because there was no net energy borrowed. From this perspective, the question of what came before is answered simply. Nothing came before, because there was nothing. The universe didn't emerge from anything. It didn't have a cause. It just is. A quantum event that happened to persist rather than vanishing like most quantum fluctuations do. This possibility bothers many people. We're used to effects having causes, to things needing explanations. The idea that the entire universe could be uncaused, that it simply popped into existence for no reason at all, seems to violate basic logic. But quantum mechanics has been violating our intuitions about what's possible for 100 years, and it keeps being right. Still, even this scenario makes assumptions. It assumes quantum mechanics applies beyond space-time. It assumes the laws of physics themselves don't need an explanation. Where did those laws come from? Why does quantum mechanics work the way it does? Why is there something rather than nothing? These questions might not have answers, at least not answers we can access. We're part of this universe, built from its matter, following its laws. Asking us to explain why the universe exists might be like asking a character in a novel to explain why the author wrote the book. We're inside the system trying to understand the system itself. Yet we keep trying. Because that's what consciousness does. We look around, see patterns, and ask why. The same drive that made ancient humans wonder about thunder and stars now has us calculating quantum field theories and analyzing cosmic radiation. The tools have changed, the questions remain, and slowly we're learning. Not just about what happened after the Big Bang, but about the nature of time, causality, and existence itself. Each model, Each theory, each observation adds another piece to the puzzle. We may never see the complete picture, but we're definitely seeing more than we did before. The cosmic microwave background holds clues we're still decoding. Gravitational wave detectors might catch echoes from before the Big Bang if certain cyclic models are correct. Particle accelerators probe the fundamental forces that shaped the early universe. Quantum computers might help us simulate conditions we can't reproduce in laboratories. The tools keep improving. The data keeps accumulating. What we're discovering suggests the universe is stranger than we imagined. Time might not be what we think it is. Causality might work differently at fundamental scales. Our Big Bang might not be unique. The boundary between something and nothing might be blurrier than we assumed. These aren't comfortable answers. They don't satisfy our desire for simple explanations or ultimate causes, but they're honest answers based on what the mathematics and observations actually tell us. And they're provisional, subject to change as we learn more. That's the nature of science. We build models, test them, revise them. We're always wrong in some way, but we're getting less wrong over time. Our current theories about the early universe are surely incomplete, maybe fundamentally mistaken in ways we haven't realized yet. But they're better than what came before, and what comes next will be better still. The question of what preceded the Big Bang might not even be the right question. Maybe we should ask, what is the nature of existence such that universes can occur? What are the fundamental principles that make reality possible? Why do mathematical laws govern physical behavior? These questions go deeper than asking about temporal sequences or causal chains. Some physicists and philosophers think consciousness itself might be part of the answer. Not in a mystical sense, but in recognizing that the universe has evolved structures capable of self-reflection. We're not outside observers studying an alien cosmos. We're the universe examining itself, using matter to understand matter, using natural laws to discover natural laws. This recursive quality might be essential. Maybe universes that produce observers are fundamentally different from universes that don't. Maybe the fact that we're here asking these questions is itself a clue about what kind of universe we inhabit. The anthropic principle suggests we naturally find ourselves in a universe compatible with our existence, but maybe it goes deeper. Maybe observer-producing universes are the only kind that can exist in some meaningful sense. These ideas blur the line between physics and philosophy, and that might be appropriate. At the very edge of what we can know, where our best theories break down and our observations can't reach, scientific and philosophical questions merge. We're not just asking what happened, but what it means for anything to happen, what existence itself requires. The honest answer remains, we don't fully know what came before the Big Bang, or if that question even makes sense. But we know vastly more than we did a century ago. We have mathematical frameworks that describe the universe back to its first moments. We have observations confirming those frameworks. We have theories that extend beyond the Big Bang, making testable predictions. We're still in the middle of this investigation. The story isn't finished. New telescopes will probe deeper into cosmic history. New theories will offer fresh perspectives. New experiments might reveal physics we haven't imagined yet. The question that seemed purely philosophical is becoming increasingly scientific, accessible to observation and calculation rather than just speculation. And whatever we discover, it will likely be stranger than we expect. Every time we've pushed the boundaries of knowledge, reality has surprised us. Quantum mechanics revealed a probabilistic universe when everyone expected clockwork determinism. Relativity showed space-time was flexible when everyone thought it was rigid. The Big Bang itself shocked scientists who assumed the cosmos was eternal and unchanging. What lies beyond the Big Bang, or before it, or instead of it, will probably shock us too. The universe has a habit of being more interesting than our theories, but that's what makes the search worthwhile. We're not just accumulating facts. We're discovering what kinds of things can be true, expanding our sense of what's possible. Curiosity has taken us to the edge of the observable universe and back to its first moments. Now we're asking what lies beyond that edge, before that beginning. The answers, when they come, will reshape how we understand everything. But there's something else happening here, something that goes beyond just solving cosmic puzzles. Every question we ask about the universe's origins is also a question about ourselves. We're made of atoms forged in stellar furnaces. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all came from stars that lived and died billions of years ago. You're not just in the universe, you're made from it, assembled from the debris of cosmic events so ancient they predate Earth itself. This connection runs deeper than chemistry. The laws that govern the Big Bang are the same laws that govern your heartbeat. The quantum mechanics that describes particle behavior in the early universe also describes the electrons in your neurons. The forces that shaped galaxies also shape every molecule in your body. There's no separation between you and the cosmos. You're a localized expression of universal processes, a way for the universe to examine itself. When you ask what came before the Big Bang, you're exercising capacities that took 13.8 billion years to develop. The universe had to expand and cool, form stars and galaxies, create heavy elements, assemble planets, evolve life, develop nervous systems, and finally produce brains capable of contemplating their own cosmic origins. Your ability to wonder about the Big Bang is itself a product of the Big Bang. This creates a strange loop. The universe produces observers who study the universe, who discover their products of what they're studying. It's like a story that writes itself into existence, or a painting that paints itself. The observer and observed aren't separate categories. They're different aspects of a single self-organizing system. Some physicists take this seriously as a clue about reality's nature. John Wheeler, who coined the term black hole, proposed what he called the participatory anthropic principle. He suggested that observers aren't passive witnesses to a pre-existing universe, but active participants in bringing it into being. Not in a mystical sense, but through the quantum mechanical principle that measurement affects reality. If the universe is fundamentally quantum, and quantum systems don't have definite properties until measured, then maybe observers play a necessary role in actualizing the cosmos. This sounds bizarre, but quantum mechanics is bizarre. An electron doesn't have a definite position until you measure it. Before measurement, it exists in a superposition of possible locations. The act of observation collapses these possibilities into a single actuality. If this applies to electrons, why not to the entire universe? Maybe the cosmos exists in a superposition of possible histories until observers emerge to collapse those possibilities into the one history we experience. Wheeler pushed this further. He imagined the universe as a self-excited circuit. Quantum events in the early universe created conditions for observers to evolve. Those observers make measurements that retroactively give definite properties to quantum events in the past. The past and present form a loop, each making the other possible. The universe pulls itself into existence by its own bootstraps. Most physicists find this too radical, but it illustrates how deeply strange the territory becomes when we ask what came before the Big Bang. We're not just asking about events in time. We're asking about the nature of time, existence, causality, and consciousness. These questions interconnect in ways that blur traditional boundaries between physics and philosophy. Still, we can make progress without solving every metaphysical puzzle. Even if we don't know what came before the Big Bang, we can study what came immediately after. And what we've discovered is extraordinary. Within the first second after the Big Bang, the universe went through multiple phase transitions. Think of how water changes from ice to liquid to steam as temperature rises. Each transition reveals different properties of H2O. Similarly, as the universe cooled from its initial extreme temperatures, different forces and particles separated out. In the first trillionth of a second, the strong nuclear force separated from the electroweak force. This is when quarks and gluons became distinct entities. Before this, they were unified in a quark-gluon plasma so hot and dense that individual particles couldn't exist. By 1 microsecond, quarks combined into protons and neutrons. These are the building blocks of atomic nuclei, but they couldn't form nuclei yet. The universe was still too hot. At 1 second, neutrinos decoupled from matter. These ghostly particles rarely interact with anything, so once the universe became transparent to them, they just kept traveling. Those neutrinos are still out there, forming a cosmic neutrino background analogous to the cosmic microwave background, but even harder to detect. Between 1 and 3 minutes, nuclear fusion occurred. Protons and neutrons combined to form the first atomic nuclei, mostly hydrogen and helium, with trace amounts of lithium and beryllium. This brief window of nucleosynthesis determined the universe's chemical composition for hundreds of millions of years. No stars existed yet to make heavier elements. For the next 380,000 years, the universe was opaque. Light couldn't travel far because free electrons scattered photons constantly. It was like trying to see through fog so thick it was essentially a wall. Then came recombination. Electrons combined with nuclei to form neutral atoms. Suddenly light could travel freely. The universe became transparent, and that moment is what we see in the cosmic microwave background. It's not the Big Bang itself, but the moment the universe cleared, like fog lifting to reveal a landscape. After that came the Dark Ages. No stars yet, no galaxies, just neutral hydrogen gas slowly collapsing under gravity into denser regions. This period lasted several 100 million years. It would be unrecognizable to us, a universe without light except for the fading infrared glow from recombination. Eventually, the first stars ignited. These were probably massive, hot, and short-lived, nothing like the stars we see today. They were made purely of hydrogen and helium, with none of the heavy elements that later stars would contain. When they died, they exploded as supernovae, scattering newly created heavy elements into space. Those heavy elements made the next generation of stars different. They could form planets. They could develop complex chemistry. They could eventually support life. This is where carbon comes from. Carbon atoms don't exist at the Big Bang. They're created inside stars through a delicate process that requires precise nuclear physics. Fred Hoyle predicted this process before it was observed, realizing that life requires carbon and carbon requires stars, so stars must have a way to make it. The universe is literally configured to produce the elements needed for complexity. That's not proof of design. It's observation of what kind of universe we inhabit. A universe with different physical constants might not produce carbon or any heavy elements. Such a universe wouldn't have chemistry as we know it, couldn't form rocky planets, wouldn't develop life. We naturally find ourselves in a universe capable of producing observers because only such universes have observers to find anything. But why this universe? Why these particular physical constants? Why laws that permit complexity rather than eternal simplicity or immediate collapse? One answer is the multiverse. If countless universes exist with different physical laws, we naturally inhabit one where the laws permit our existence. It's selection bias, not design. We don't observe the vast majority of universes because they can't produce observers. Another answer questions the question. Maybe these are the only possible laws. Maybe mathematics constrains physics so tightly that only one consistent set of rules exists. We think we can imagine different laws, but maybe truly different laws would be logically incoherent, like imagining a universe where 2 + 2 = 5, or maybe the laws evolve. Lee Smolin proposed that universes reproduce through black holes, each inheriting slightly modified laws from its parent. Universes with laws that produce many black holes have more offspring. Over countless generations, this could favor universes with our kind of physics, not through design, but through cosmic natural selection. These ideas are speculative. We can't test them directly, but they show how seriously physicists take the question of why the universe is this way rather than some other way. It's not idle curiosity. It's an attempt to understand the deepest principles governing reality. Meanwhile, we keep probing what happened after the Big Bang. The James Webb Space Telescope is observing galaxies that formed just a few 100 million years after the beginning. These galaxies look different from modern ones, more compact and chaotic. We're watching cosmic evolution in action, seeing how structure emerged from near uniformity. Gravitational wave detectors are catching signals from colliding black holes and neutron stars. These violent events release information about matter under extreme conditions, approaching what existed in the early universe. Each detection is like an echo from a time before stars. Particle accelerators recreate the quark-gluon plasma that filled the universe in its first microseconds. By smashing heavy ions together at nearly light speed, we generate temperatures that haven't existed naturally since the Big Bang. It's time travel through physics, reproducing ancient conditions in modern laboratories. All this work pushes our understanding backward toward that initial moment. We've traced cosmic history to when the universe was a trillionth of a second old. Before that, our theories become uncertain. We need quantum gravity to go further, a framework that combines quantum mechanics and general relativity. We don't have that yet. Several approaches compete. String theory proposes that fundamental entities are tiny vibrating strings rather than point particles. Loop quantum gravity suggests space itself is quantized, made of discrete units rather than being infinitely divisible. Other theories explore different possibilities, each mathematically sophisticated but hard to test. The challenge is that quantum gravity affects only matter at the Planck scale, which is incomprehensibly small. The Planck length is about 10 to the minus 35 meters. The Planck time is about 10 to the minus 43 seconds. At these scales, space and time themselves become quantum and fuzzy. Our usual concepts break down. We can't build experiments that directly probe the Planck scale. The energies required vastly exceed what's possible with any conceivable technology. So we look for indirect evidence, subtle effects that quantum gravity might produce in accessible observations. The cosmic microwave background might contain signatures of quantum gravity from the very early universe. Certain particle physics experiments might reveal clues. We're searching for fingerprints rather than seeing the phenomenon directly. This is frontier science at its most challenging. We're asking questions about regimes we can't access, using mathematics that pushes human comprehension to its limits, seeking evidence in data so subtle it barely rises above noise. Progress is slow and uncertain. Careers are spent pursuing theories that might be wrong. Yet people do it because the questions matter. What came before the Big Bang? That question might be answered by quantum gravity, or it might be dissolved by a better understanding of time. But either way, pursuing it drives us to develop new physics, new mathematics, new ways of thinking about reality. Even if we never get a complete answer, we learn enormous amounts trying, and we've already learned something profound. The universe is comprehensible. That's not obvious. Reality could have been arbitrary, chaotic, impossible to understand. Instead, it follows mathematical laws we can discover and verify. Electrons behave the same way in every laboratory. Light travels at the same speed throughout the cosmos. The laws we discover here apply everywhere and everywhen we can observe. This mathematical regularity is mysterious. Why should the universe be governed by elegant equations? Why should human brains, evolved to survive on African savannas, be capable of understanding quantum mechanics and general relativity? There's no obvious evolutionary advantage to comprehending black holes or the Big Bang, yet we can. Eugene Wigner called this the unreasonable effectiveness of mathematics in the natural sciences. Math developed for pure abstract reasons turns out to describe physical reality with stunning precision. Complex numbers, invented for solving equations, turn out to be essential for quantum mechanics. Riemannian geometry, developed as mathematical exploration, becomes the language of general relativity. Over and over, pure mathematics anticipates physics. Maybe math and physics are deeply connected because physical laws are mathematical structures. Maybe the universe is math, and we're discovering its axioms and theorems. Or maybe our brains evolved to detect patterns, and we've gotten surprisingly good at it. Good enough to find patterns at scales far beyond our daily experience. Whatever the reason, it works. We can ask what came before the Big Bang and make genuine progress. We can develop theories, make predictions, gather evidence. The question isn't purely philosophical anymore. It's becoming scientific, accessible to investigation, rather than just speculation. Human knowledge has always expanded this way. Questions that seemed forever beyond reach become answerable through new tools and ideas. We learned Earth's age by understanding radioactivity. We discovered the universe's expansion by measuring distant galaxies' light. We mapped the cosmic microwave background using satellite technology. Each advance opens new territories. What seemed impossible becomes routine. Questions migrate from philosophy to physics, and the question of what came before is making that journey now. We have candidate theories, testable predictions, ongoing observations. We don't have the answer yet, but we're working on it. That's the human condition, really. Standing on a small planet, looking up at the cosmos, asking questions that should be beyond us, and sometimes, astonishingly, finding answers. The search for what came before the Big Bang represents something profound about scientific inquiry. We're not just collecting facts, we're trying to understand the deepest structure of reality. Every answer raises new questions. Each solution reveals deeper mysteries. Science doesn't close doors, it opens them. What seems like an ending is actually a beginning. Consider where we started. Ancient humans watched the sky and wondered. They created stories to explain what they saw. Sun gods and moon goddesses, creation myths and cosmic battles. These weren't primitive or stupid. They were humanity's first attempts at cosmology, using the tools available. Pattern recognition and storytelling. Then we developed better tools, mathematics, systematic observation, the scientific method. Suddenly we could test ideas against reality. Wrong theories could be discarded, correct ones refined. Progress became possible. We discovered Earth orbits the Sun, that stars are distant suns, that galaxies exist beyond our own. Each revelation expanded our cosmic address. We went from thinking Earth was the center of everything to realizing we're on a typical planet, orbiting a typical star, in a typical galaxy, in a universe containing hundreds of billions of galaxies. That journey humbled us, but it also empowered us, because we figured it out. Creatures who evolved to find food and avoid predators developed the capacity to understand black holes and quantum mechanics. We transcended our evolutionary origins. That's extraordinary. And now we're asking, what came before the beginning itself? Pushing to the absolute boundary of possible questions. If we answer it, there will be another question beyond. There always is. That's not frustrating. It's exhilarating. The universe keeps offering deeper levels to explore. Some people find this unsatisfying. They want final answers, ultimate explanations. But nature doesn't owe us closure. Reality is what it is, regardless of our preferences. And what it is turns out to be endlessly fascinating, more interesting than any answer we could have imagined. The Big Bang Theory itself shows this. Before we understood cosmic expansion, people assumed the universe was eternal and unchanging. That seemed obvious. How could reality have a beginning? Beginnings require causes. And what could cause everything? Then, Hubble discovered galaxies are moving apart. Einstein's equations predicted it, but even Einstein initially resisted. He added a fudge factor to keep the universe static. When observations proved expansion, he called it his greatest blunder. But it wasn't a blunder. The cosmological constant, that fudge factor, turned out to be real. We call it dark energy now. It's causing cosmic expansion to accelerate. Einstein's mistake predicted something we only confirmed decades after his death. Science works like that. We stumble forward, making errors, correcting them, occasionally getting things right for the wrong reasons. It's messy and human, But it works. Our theories get better. Our understanding deepens. The question of what came before the Big Bang fits this pattern. We're in the messy middle stage. Lots of ideas, limited evidence, vigorous debate. Some current theories will prove wrong. Others might be right in unexpected ways. We'll probably end up somewhere we don't anticipate. That's fine. The journey matters as much as the destination. Each step forward, even the missteps, teaches us something. We're learning how to think about quantum gravity, how to merge relativity with quantum mechanics, how to test theories at scales we can't directly access. These skills will serve us regardless of whether we answer the original question. And we're learning something deeper. We're learning about the nature of time itself. Is time fundamental or emergent? Does it have a beginning? Can it exist without space? These questions seemed purely philosophical. Now they're becoming physical. We can make mathematical models and see what they predict. Time might not be what we think. Our experience of time flowing from past to future might be an illusion, a consequence of entropy and memory, not a fundamental feature of reality. The equations of physics work equally well forward or backward. Time's arrow emerges from statistics and thermodynamics, not from time itself. If time is emergent rather than fundamental, asking what came before time began is like asking what's north of the North Pole. The question dissolves under examination, not because we can't answer it, but because it's based on incorrect assumptions about time's nature. This possibility is intellectually unsettling. We experience time so directly. Past, present, future seem obviously real and distinct. Learning that this experience might not reflect reality's deep structure is disorienting. Like discovering the ground beneath our feet is actually moving, that Earth spins and orbits and hurdles through space. But unsettling doesn't mean wrong. Reality doesn't conform to our intuitions. Our intuitions evolved for survival, not truth. They work fine for everyday experience, but break down at extremes. Quantum mechanics violates our intuitions constantly. So does relativity. Yet both theories are fantastically accurate. We're probably experiencing the same thing with time. Our intuitive understanding works for daily life, but fails at cosmic scales. That's okay. We can develop new intuitions. Scientists working with relativity eventually develop a feel for space-time geometry. Quantum physicists get comfortable with superposition and entanglement. The math becomes intuitive through practice. Future physicists might develop intuitions about emergent time or quantum gravity. What seems bizarre to us might feel natural to them. They'll wonder why we found it confusing. Just as modern physicists wonder why people once struggled with heliocentrism or evolution, human understanding evolves. We're not fixed in our current knowledge. Each generation inherits previous discoveries and pushes further. Questions we're wrestling with now might be textbook material in a century. Students will learn the answers as established fact, barely noticing how strange they are. And those students will face new mysteries, deeper questions we haven't imagined yet. That's how science works. Progress doesn't mean running out of questions. It means asking better questions. More precise, more fundamental, harder to answer. What came before the Big Bang is a better question than, why does the sun move across the sky? We've progressed from explaining daily observations to probing the universe's origin. That's advancement. Not because we're smarter than our ancestors, but because we've accumulated knowledge and tools they lacked. We stand on their shoulders. Every generation builds on previous work. Newton famously said, "If I have seen further, it is by standing on the shoulders of giants." That's not modesty, it's accurate. Science is cumulative. Each contribution adds to the whole. The question of what came before the Big Bang builds on centuries of work. Newtonian mechanics, thermodynamics, electromagnetism, quantum mechanics, general relativity, particle physics, cosmology. All these fields contribute to current theories. We're not starting from scratch. We're extending an edifice built over generations, and future scientists will extend it further. They'll have better telescopes, more powerful computers, new mathematical tools. They'll see things we can't. They'll test theories we're developing now. Some will be confirmed, others discarded. New theories will emerge. This is the scientific process: hypothesis, prediction, observation, revision, round and round, gradually converging on truth. We never reach perfect knowledge, but we get closer. Our models become more accurate, our predictions more reliable. The Big Bang Theory itself demonstrates this. It started as a speculation based on Einstein's equations. Then Hubble discovered cosmic expansion. Then we predicted and found the cosmic microwave background. Then we measured temperature fluctuations that match inflation predictions. Each observation refined the theory, made it more precise, more tested, more trustworthy. We'll do the same with quantum gravity and what came before. Develop theories, make predictions, gather evidence, refine ideas. It might take decades or centuries, but we're making progress. The question is becoming answerable. Some people ask why it matters. Why spend resources investigating the universe's origin when we have problems here on Earth? Poverty, disease, conflict. Shouldn't we focus on those? This is a false choice. We can do both. Humanity is capable of multiple projects simultaneously, and basic research often produces unexpected benefits. GPS requires relativistic corrections. MRI machines use quantum physics. The internet grew from particle physics research. Tang came from the space program. Okay, that last one isn't impressive, but the pattern holds. Basic research pays off in unpredictable ways. More fundamentally, asking questions about our origins is part of what makes us human. We're the species that looks up and wonders, that tries to understand our place in the cosmos. That's not frivolous. It's essential to who we are. Every culture asks these questions. Where did we come from? Why are we here? What's our purpose? Religion provides answers. Philosophy explores them. Science investigates them empirically. Different approaches, same fundamental human need to understand. And the answers matter. Learning we're not the center of the universe changed how we see ourselves. Understanding evolution transformed biology and medicine. Discovering the Big Bang revealed our cosmic history. Each advance shapes our worldview. Learning what came before the Big Bang will do the same. It will tell us something profound about reality's nature, about time, space, existence itself. That knowledge will ripple through philosophy, theology, culture. It will change how we think about beginnings and endings, about causation and existence, and it might have practical applications we can't foresee. Quantum gravity could revolutionize technology. Understanding space-time at the Planck scale might enable things currently impossible. We don't know. That's why we investigate. The history of science is full of discoveries that seemed purely theoretical but became intensely practical. Maxwell's equations of electromagnetism were mathematical curiosities. Now, they're the foundation of electrical engineering. Quantum mechanics seemed like philosophical weirdness. Now it's essential for electronics and computing. Maybe quantum gravity will follow the same path. From abstract theory to practical application. From useless knowledge to technological revolution. Or maybe it won't. But we'll never know unless we pursue the question. And the pursuit itself has value. Training physicists to think about quantum gravity develops skills applicable elsewhere. The mathematical tools created for these problems get used in other fields. The technologies developed for testing theories find unexpected applications. Science is an ecosystem. You can't predict which part will prove most valuable. Basic research feeds, applied research feeds, technology feeds, economy feeds, society. It's all connected. Cutting basic research to fund immediate applications is short-sighted. You're eating your seed corn. Societies that invest in fundamental research thrive. They develop new technologies, attract talented people, create economic opportunities. It's not charity, it's investment in the future. And beyond economics, there's culture. Societies that value knowledge, that ask deep questions, that push boundaries. These societies flourish intellectually and creatively. Science and art and philosophy reinforce each other. They're all ways of exploring reality and human experience. The question of what came before the Big Bang sits at the intersection of science, philosophy, and culture. It's simultaneously a physics problem, a philosophical puzzle, and a question of cultural meaning. Answering it requires technical expertise, conceptual creativity, and deep thought about existence. This is science at its best. Not just calculating numbers, but grappling with profound questions. Not just gathering data, but seeking understanding. Not just describing nature, but revealing its deepest patterns. And we're privileged to live in an era when this question is becoming answerable. Previous generations could only speculate. Future generations might take the answer for granted. We're in the middle, watching the mystery yield to investigation. That's exciting. Every few years brings new data, better observations of the cosmic microwave background, more precise measurements of cosmic expansion, improved tests of general relativity, advances in quantum theory. Slowly, steadily, we're constraining the possibilities, ruling out some theories, supporting others. Quantum gravity remains elusive. We don't have a complete theory yet, but we're making progress. String theory, loop quantum gravity, causal set theory, various approaches are being explored. One might prove correct, or we might need to synthesize ideas from several. Or someone might develop a completely new approach. That's how breakthroughs happen. Usually not through sudden inspiration, but through gradual accumulation of ideas and evidence. Then someone sees a pattern others missed, makes a connection that seems obvious in retrospect, and suddenly everything clicks into place. We might be close to that moment, or it might be decades away. There's no way to know. Scientific breakthroughs are unpredictable. You can't schedule insight, but the work continues. Theorists develop models. Experimentalists gather data. Observational astronomers map the cosmos with ever greater precision. Each contribution adds to our understanding. And somewhere in all this effort, the answer to what came before the Big Bang is emerging. It might not happen in our lifetimes. That's worth acknowledging. Some questions take generations to answer. Plate tectonics was proposed in the early 1900s, but wasn't accepted until the 1960s. Continental drift seemed absurd to most geologists for decades. Then seafloor spreading was discovered and everything changed. Sometimes you need new technology before theory can be tested. Sometimes you need a conceptual shift before evidence makes sense. The question of before the Big Bang might be like that. We might have the answer already, buried in equations we don't fully understand. Or we might be missing something fundamental. A new principle of nature we haven't discovered yet. Consider what happened with quantum mechanics. In the 1920s, physicists were stuck. Classical physics couldn't explain atomic spectra or black body radiation. Weird experimental results kept piling up. Then Heisenberg and Schrödinger developed quantum mechanics. Not because they had a grand vision, but because they were trying to make sense of data. The theory emerged from necessity, and it was bizarre. Particles behaving like waves, probabilities instead of certainties, measurement affecting reality. Nobody liked it at first. Einstein spent decades trying to disprove it, but it worked. Predictions matched experiments with incredible precision. Eventually everyone accepted it because nature left no choice. Quantum gravity might unfold the same way. We're gathering puzzling observations, black hole information paradoxes, quantum entanglement across cosmic distances, the accelerating expansion of the universe. Each hints that our current theories are incomplete. Combine enough hints and eventually someone connects them, sees the pattern everyone else missed, proposes a theory that seems crazy at first but explains everything elegantly. That's when paradigm shifts happen, when accumulated anomalies reach critical mass, when the old framework can't stretch any further, when someone young and bold enough proposes something radically new. We might be approaching that point, or not. There's no way to tell from inside the process. Future historians will trace the path clearly. They'll see which papers mattered and which were dead ends. They'll identify the crucial insights and pivotal experiments. But we're living through it, swimming in a sea of possibilities with no map to the shore. Some find that frustrating. Others find it exhilarating. The frontier of knowledge is messy and uncertain. That's what makes it a frontier, and regardless of when we answer the question, the asking itself matters. Think about what we've learned by pursuing it. We've developed sophisticated models of the early universe, mapped the cosmic microwave background in exquisite detail, discovered dark energy, measured the geometry of space, pushed quantum mechanics to its limits, all from asking what came before. Even if the ultimate answer remains elusive, the journey has been productive. This is how science advances, not through linear progress toward predetermined goals, but through exploration of interesting questions. You pursue what seems important or fascinating. You develop tools and theories. You gather data. Sometimes you answer your original question. Sometimes you discover something completely unexpected. The history of science is filled with accidental discoveries, things found while looking for something else. Cosmic microwave background radiation was discovered by accident. Scientists were trying to eliminate noise from a radio telescope. They kept finding this persistent signal from every direction. Eventually they realized they were detecting the afterglow of the Big Bang. Nobel Prize-winning discovery that wasn't even the goal of the research. Who knows what we'll stumble upon while investigating quantum gravity? Maybe a new form of matter, maybe insights into quantum computing, maybe applications nobody can imagine yet. The path from basic research to practical application is rarely straight, but it exists. Transistors came from quantum mechanics. GPS requires general relativity. Lasers emerged from understanding atomic physics. Technologies that shape modern life all trace back to people asking abstract questions about nature. So when someone asks why we should care about what came before the Big Bang, there's a practical answer. Because pursuing fundamental questions drives technological progress. And there's a deeper answer. Because we're humans, and humans ask questions. We're curious. We seek understanding. We want to know how things work and why they are the way they are. That's not optional. It's core to who we are as a species. Every culture throughout history has asked questions about origins. Creation myths exist everywhere. Different stories, different gods, different mechanisms. But the impulse is universal. Humans need origin stories. We need to understand where we came from and how we got here. Science is our most recent and most successful approach to answering those questions. It uses evidence and logic instead of tradition and authority. But it's serving the same fundamental human need. What came before the Big Bang is our generation's creation myth. Future generations will either know the answer or have pushed the mystery back further. Either way, they'll have their own questions. There's always another layer, always something deeper to explore. That's not a bug, that's a feature. An infinite universe of questions means we'll never run out of things to wonder about, never reach the end of knowledge, and have nothing left to discover. Some people find that unsettling. They want final answers, complete understanding, a theory of everything that explains everything and requires no further investigation. But that's a fantasy. Even if we discovered such a theory, it would raise new questions. Why this theory and not another? Why do these laws exist? Why is there something rather than nothing? You can always ask another why. There's no ultimate foundation where questioning stops. It's questions all the way down, and that's beautiful. It means science will never be finished. There will always be mysteries to explore, always frontiers to push, always questions for curious minds to tackle. What came before the Big Bang is just one question among countless others, but it's a good one, deep and profound, connecting physics and philosophy, pushing our theories to their limits, forcing us to think carefully about space and time and causality and existence. The answers we eventually find might be surprising. They usually are. Nature rarely works the way we initially expect. Classical physics made sense, quantum mechanics doesn't. But quantum mechanics is more accurate. General relativity is bizarre. Curved space-time, time dilation, but it's correct. Predictions match observations. Nature doesn't care about our intuitions. It operates according to its own principles. Our job is to figure out what those principles are. That requires humility. We have to be willing to abandon cherished ideas when evidence contradicts them. Have to accept that reality might be stranger than we imagined. Have to follow the data wherever it leads, even if we don't like the destination. That's hard. Humans naturally resist changing their minds. We get attached to theories, invest our careers in particular approaches, build communities around shared assumptions. When evidence challenges those assumptions, it's uncomfortable, sometimes threatening, but science advances by overcoming that discomfort, by valuing truth over comfort, evidence over authority, what works over what we wish were true. The question of what came before the Big Bang tests that commitment. Because the honest answer right now is we don't know. We have speculations, educated guesses, tentative theories, but not certainty. And admitting uncertainty is difficult. There's pressure to have answers, to sound confident, to reassure people that science has everything figured out. But that's not how science works. Science is comfortable with uncertainty. It's a feature, not a bug. Uncertainty means there's still work to do, still questions to answer, still room for discovery. And the uncertainty around this question is particularly profound. We're not just uncertain about details, we're uncertain about fundamentals. What is time? What is space? What is causality? These aren't minor technical questions. They're deep conceptual issues. Questions that philosophers have grappled with for millennia. Questions that might not have simple answers, or might have answers that require rethinking everything we thought we understood. That's exciting. It means we're not just filling in details of a known picture. We're potentially discovering an entirely new picture, a new way of understanding reality. That doesn't happen often. Most science is incremental, small steps forward, refining existing theories, measuring constants more precisely. But occasionally there are revolutions, moments when the entire framework shifts. When we realize we were looking at things backwards, when a new perspective reveals patterns we couldn't see before. Maybe we're approaching such a moment. Maybe the question of what came before the Big Bang will force us to reconceptualize time itself, to see it not as a fundamental feature of reality, but as something emergent, something that arises from deeper processes, like temperature emerging from molecular motion, or pressure emerging from particle collisions. Maybe time is similar, a useful concept at large scales but not fundamental at the deepest level. If so, asking what came before time began is the wrong question, like asking what's north of the North Pole. The question assumes a framework that doesn't apply. Or maybe time is fundamental but has properties we don't understand. Maybe it can branch or loop or have more dimensions than we experience. Maybe our intuitive understanding of time as a one-dimensional flow from past to future is oversimplified. Maybe reality is more complex. And maybe understanding that complexity will answer the question. Show us what came before by revealing that before means something different than we thought. These are speculations, but they're informed speculations, based on hints from quantum mechanics and general relativity, based on attempts to reconcile theories that seem incompatible, based on patterns other scientists have noticed. They might be wrong, probably are wrong in some details, but they point in interesting directions, suggest avenues worth exploring. And that's how progress happens, through informed speculation followed by rigorous testing, through creative hypotheses confronted by hard evidence, through imagination constrained by mathematics. The interplay between creativity and rigor is essential. Pure speculation without constraints leads nowhere. Pure rigor without creativity makes no progress. You need both. You need people who can imagine radical possibilities, and you need people who can test those possibilities against reality. Science at its best combines both impulses, wild ideas carefully examined, rigorous analysis opening new conceptual space. What came before the Big Bang demands both. It requires creative thinking because conventional approaches don't work. The question pushes beyond where our theories have been tested, into regimes where new principles might operate. But it also requires rigorous analysis, careful mathematical modeling, precise experimental tests where possible. We can't just make up stories. We need stories that match evidence, that make testable predictions, that connect to what we already know while extending beyond it. That's a delicate balance, and it's why progress is slow, why we don't have the answer yet despite decades of work. The question is genuinely hard. It requires both technical sophistication and conceptual innovation. It sits at the intersection of multiple fields: general relativity and quantum mechanics and cosmology and philosophy. Understanding it requires synthesizing insights from all these areas. Few people have expertise across that range, and even those who do face fundamental challenges. The mathematics is difficult. The concepts are subtle. The experimental constraints are limited, but that's what makes it worth doing. Easy questions get answered quickly. Hard questions persist. The question of what came before the Big Bang is hard because it touches something deep, not just about physics, but about the nature of existence itself. Why is there something rather than nothing? Why these laws and not others? Why a universe at all? These questions have troubled philosophers for millennia. Now they're becoming scientific questions too, answerable through observation and experiment rather than pure reason. That's progress. Not because science is better than philosophy, but because we've reached a point where these deep questions connect to testable predictions, where abstract speculation meets concrete evidence, where what seemed purely metaphysical becomes partially physical. The boundary between philosophy and science was always fuzzy. Questions migrate across it. What was once philosophy becomes science as we develop tools to investigate it. What was once science becomes philosophy as we recognize deeper questions beneath the answers. What came before the Big Bang straddles that boundary. It's partly a physics question about the early universe, partly a philosophical question about the nature of time, partly a mathematical question about the structure of theories. Answering it requires insights from multiple domains, collaboration across disciplines, willingness to think both technically and conceptually, to be rigorous and creative, precise and imaginative. That's hard, but it's also exactly what makes the questions so compelling. And we're making progress. Maybe not as fast as we'd like, maybe not in the ways we expected, but progress nonetheless. Every year brings new observations, better measurements, refined theories. The space of possibilities is shrinking. We're ruling out some options, constraining others, gradually zeroing in on the answer, or discovering that the question needs to be reformulated. Either way, we're learning, advancing our understanding, getting closer to truth. Sometimes the most profound insights come from unexpected directions, not from the center of a field, but from its edges, where different disciplines meet and cross-pollinate, where established methods encounter their limits and something new must emerge. Consider how quantum mechanics was born, not from extending classical physics, but from recognizing its failure. Planck didn't want to quantize energy. He tried every conventional approach first. Only when nothing else worked did he introduce his radical constant. That desperate move became the foundation of a revolution. Maybe that's where we are with the question of what came before the Big Bang. Conventional approaches have taken us far. General relativity describes gravity beautifully. Quantum mechanics explains the microscopic world with stunning precision. Together, they account for nearly everything we observe. But they break down at the beginning, at the singularity where the Big Bang supposedly started. That breakdown isn't a bug, it's a feature. It's telling us something important, that our theories are incomplete, that new physics waits to be discovered, that the question of what came before requires tools we haven't fully developed yet. This realization shifts how we think about the problem. Instead of asking what came before the Big Bang, given our current theories, we should ask what theories would make that question answerable. What framework would let us peer behind the curtain? What principles would extend our understanding beyond the singularity? Several candidates exist. Each offers a different way to resolve the beginning. Each suggests different physics operating in that extreme regime. Each makes different predictions we might someday test. Loop quantum gravity says space itself is quantized. At the smallest scales, it's not smooth but grainy, made of discrete units called loops. When you try to compress space to infinite density, quantum effects create a repulsive force. The Big Bang becomes a big bounce. The universe contracts to a minimum size, then rebounds. What came before was a previous universe, older, perhaps very different, but connected to ours through the bounce. String theory offers another perspective. It says fundamental particles aren't points, but tiny, vibrating strings. These strings exist in more than 4 dimensions. Most of those dimensions are curled up, too small to see. But in the extreme conditions near the Big Bang, extra dimensions might have been larger. The universe might have emerged from colliding higher dimensional objects called brains. What came before was a higher dimensional space. Our universe is a 3-dimensional slice through something bigger. Eternal inflation proposes that our Big Bang was one bubble in an endless sea of bubbles. Inflation never stops globally. It only stops locally in certain regions. Each region where inflation stops becomes a universe, with its own physics potentially, its own constants, its own history. What came before our Big Bang was the inflating space from which our bubble emerged. And that space has been inflating eternally. No beginning at all. Each theory tells a different story. Each requires different mathematics. Each suggests different observations we might make to test it. But they share something important. They all treat the Big Bang not as an absolute beginning, but as a transition. A moment when our observable universe began. But not necessarily when everything began. This shift in perspective is subtle but profound. It transforms the question. Instead of asking what caused the universe, we ask what caused our local patch of it. Instead of explaining existence itself, we explain the particular form existence takes here and now. That's more tractable, more scientific, more answerable. Yet it opens new questions. If our universe emerged from something else, what is that something? What are its properties, its laws, its history? And if that something has always existed, why? What determines its nature? Why that particular eternal state rather than some other? We've pushed the mystery back a level, not eliminated it. That's often how science progresses. Answering one question reveals deeper ones beneath it. Understanding breeds new puzzles. Each solution opens new territory to explore. Some find this frustrating. We wanted the answer to what came before the Big Bang. Instead, we get more questions, more possibilities, more uncertainty. But that's exactly what progress looks like at the frontier. Clarity comes later, after the new territory is mapped, after the possibilities are tested and refined, after evidence accumulates and guides us. Right now, we're in the exploration phase, trying different approaches, building different models, seeing what works and what doesn't. It's messy, uncertain, full of dead ends and false starts. But it's also exciting, because we're genuinely pushing into unknown territory, asking questions nobody could have formulated a century ago, using tools that didn't exist a generation ago. The tools matter. Theoretical progress requires mathematical sophistication, but it also requires observational data, experiments, measurements, ways to test our ideas against reality. For questions about the universe's beginning, that's challenging. We can't rerun the Big Bang, can't manipulate the conditions, can't set up controlled experiments, but we can observe. The cosmic microwave background carries information from when the universe was young. Tiny fluctuations in its temperature map the density variations that grew into galaxies. Those fluctuations themselves might carry signatures from even earlier, from the inflationary epoch, perhaps even from whatever preceded it. Gravitational waves offer another window. These ripples in space-time from violent cosmic events might include primordial gravitational waves from the Big Bang itself. Detecting those would probe conditions at the universe's beginning, potentially revealing what kind of physics operated then, whether it matches our theories or surprises us. Particle physics provides constraints too. The matter we see behaves certain ways, has certain properties. Those properties depend on conditions in the early universe. By studying particles now, we learn about the environment where they formed. That tells us something about what the universe was like moments after the Big Bang. And that constrains what could have come before. Each piece of evidence narrows the possibilities, eliminates some scenarios, makes others more plausible. Gradually, we're building a picture, not complete yet, not certain, but increasingly detailed and testable. This is how science works at its best, not through sudden revelations, but through patient accumulation, observations suggesting theories, theories predicting observations, the cycle repeating, each iteration refining our understanding, sometimes confirming expectations, sometimes surprising us and forcing rethinking. The question of what came before the Big Bang is embedded in that process. We don't have the answer yet, but we have better questions than before, more refined theories, more relevant data. We're closer to understanding than we've ever been, even if we're not there yet. And maybe we'll never fully get there. Maybe some aspects will remain forever beyond our grasp, limited by the nature of the universe itself, by what information has been preserved or erased, by what can in principle be observed versus what's fundamentally hidden. That possibility doesn't invalidate the effort. Understanding has value even when incomplete. Knowing the limits of knowledge is itself a form of knowledge. Recognizing what we can't know helps us focus on what we can. It shapes our questions, guides our investigations, prevents us from chasing impossibilities. Philosophy has long grappled with questions about existence and causation. Why is there something rather than nothing? What grounds the laws of nature? Can causes extend infinitely backward, or must there be a first cause? These questions predate science by millennia. They've troubled every generation of thinkers. What's new is that some of these ancient questions now connect to physics, to testable predictions and observable consequences. That doesn't mean philosophy becomes obsolete. It means the boundary between philosophy and science shifts. Some questions migrate from one domain to the other. New philosophical questions emerge from scientific discoveries. The relationship between time and causation is like that. Philosophers have always debated whether time requires change or change requires time, whether time could have a beginning, whether causality is fundamental or emergent. Now physicists contribute to those debates, not by pure reasoning but through theories and observations, by discovering that time behaves strangely near black holes, that it might be quantized, that it's relative rather than absolute. These discoveries don't settle the philosophical questions, but they constrain them. They show which possibilities are consistent with reality, which intuitions need revision, how abstract concepts connect to concrete phenomena. That's progress, even if it's not resolution. The same applies to questions about the universe's origin. Philosophy can explore logical possibilities. What could in principle exist? What makes sense conceptually? But physics determines what actually exists, what the universe actually chose from the space of possibilities. That narrows the field dramatically. Yet physics can't answer why the universe made those choices, why these laws rather than others, why anything at all. Those questions might be inherently metaphysical, beyond the reach of empirical investigation. Or maybe they'll someday become physical too. Maybe deeper theories will explain what now seems arbitrary. Maybe patterns we haven't recognized will emerge. History suggests staying humble about what's answerable. Questions that seemed purely philosophical have become scientific, and questions that seemed straightforwardly empirical have revealed philosophical depths. The boundary is fluid. What matters is continuing to ask, to probe, to test ideas against reality while remaining open to revising them. What came before the Big Bang sits at that boundary, partly empirical, partly conceptual, requiring both scientific rigor and philosophical clarity. That makes it difficult, but also rich, multifaceted, worth approaching from multiple angles. Different researchers emphasize different aspects. Some focus on mathematical consistency, building theories that work logically, that connect smoothly to what we know. Others prioritize observational tests. What can we measure that would distinguish between possibilities? How can we gather evidence about something so far in the past? Both approaches are necessary. Theories without observations are speculation. Observations without theories are just data. We need the interplay. Observations motivating theories. Theories predicting observations. Each discipline informing the other. And we need patience. Questions this deep don't yield quickly. The timescale for progress is decades, not years. Careers, not papers. We're building understanding piece by piece. Each contribution small but cumulative. Each researcher adding their part to a collective effort spanning generations. That's both humbling and inspiring. Humbling because no individual will solve this alone. Inspiring because we're part of something larger, contributing to humanity's understanding, advancing knowledge that will outlast us. The question of what came before the Big Bang connects us to that long tradition of humans wondering about origins, seeking to understand where we came from, why we're here, what it all means. Those questions are ancient, universal across cultures, fundamental to human consciousness. What's changed is our ability to investigate them scientifically, to move beyond speculation to evidence, beyond stories to theories, beyond tradition to discovery. That's the gift of the scientific method. Not that it answers all questions, but that it provides a systematic way to make progress on answerable ones. And it reveals which questions might be unanswerable. Not because we're not smart enough, but because the universe doesn't contain the information we'd need. Because some aspects of reality are fundamentally uncertain, or hidden, or lost to time. Recognizing those limits is part of understanding too. So where does this leave us? With a question that's partly answered and partly open. We understand the universe from fractions of a second after the Big Bang. We have theories about what came before, testable predictions, ongoing observations, gradual progress toward deeper understanding. But we don't have certainty, don't have the complete picture, don't know which theory is right or whether any current theory captures the truth. We're still exploring, still discovering, still being surprised by what we find. And that's exactly where we should be, at the frontier of knowledge, pushing boundaries, asking hard questions, not knowing all the answers but knowing how to search for them. That's the human project at its best. Curiosity meeting rigor, imagination constrained by evidence, wonder disciplined by method. What came before the Big Bang? We're working on it, every day, in observatories and laboratories, through calculations and simulations, by thinking carefully and testing thoroughly, building understanding step by step, getting closer to truth even if we never fully arrive. That journey matters more than the destination. Because in pursuing these questions, we learn not just about the universe, but about ourselves. About what we can know and how we know it. About the tools we've developed and the limits we face. About our place in the cosmos and our capacity to understand it. And maybe that's the real answer to our question. Not a specific theory or mechanism, but an understanding that some mysteries invite exploration more than resolution. The Big Bang might be one of those boundaries where physics meets philosophy, where science bumps against its own foundations. Consider what we're actually asking. Before implies time. But time began with the Big Bang. So before the Big Bang is like asking what's north of the North Pole. The question contains its own impossibility, yet we keep asking it. And that persistence reveals something about human nature. We're uncomfortable with beginnings that have no cause, with effects that have no prior state. Our minds rebel against it. Every experience we have involves causation, one thing leading to another. Past determining present, causes preceding effects. That's how we navigate reality, how we make sense of the world. So when physics suggests time itself might have a beginning, we struggle to accept it. It violates our deepest intuitions about how things work. But the universe doesn't owe us intuitive answers. It operates according to its own rules. Rules we discover through observation and mathematics, not through what feels right or makes comfortable sense. Quantum mechanics taught us that. Particles in two places simultaneously, effects preceding causes at small scales, reality fundamentally probabilistic rather than determined. We learn to accept those counterintuitive truths because the evidence demanded it. The experiments were clear. The mathematics was consistent. Our intuitions were wrong. Maybe the Big Bang is similar. Maybe time having a beginning is just another counterintuitive truth, one we need to accept, even though it feels strange. Or maybe not. Maybe our current understanding is incomplete. Maybe there's a deeper theory waiting, one that extends beyond the Big Bang. That explains what we currently call the beginning. That resolves the paradoxes and answers the questions. That's the exciting possibility, that we haven't reached the end of discovery. Loop quantum gravity suggests one path forward. It modifies Einstein's equations at extremely small scales, introduces quantum effects into the fabric of space-time itself, and in that framework, the Big Bang becomes a bounce, a transition from a previous contracting phase. Time extends backward beyond what we currently call the beginning. String theory offers another approach, multiple dimensions beyond the familiar four, membranes colliding in higher dimensional space. Each collision creating what looks like a Big Bang from within the resulting universe. Our beginning would be one event in a larger structure. Time would extend beyond our cosmic horizon. Eternal inflation provides yet another framework. Quantum fluctuations creating bubble universes, each bubble with its own Big Bang, ours just one among countless others. Before our Big Bang, there was the inflating field. Before that, perhaps something else, an infinite regress of structure and causation. These theories remain speculative. We lack direct evidence, can't observe beyond our cosmic horizon, can't probe the first moments directly, but we can test their predictions. Look for signatures they'd leave, patterns in the cosmic microwave background, gravitational wave signatures, correlations in large-scale structure. That's how science progresses at the frontier. Build theories, derive predictions, design observations, test and refine. Gradually narrow the possibilities, rule out what doesn't work, strengthen what survives testing. Move toward truth, even when certainty remains distant. The process requires patience. These are multi-generational questions. The observations take decades to complete. The analysis requires years. The theoretical framework evolves slowly. No single paper or discovery will resolve everything. Progress accumulates gradually, but that gradual accumulation is real. We understand vastly more than previous generations, can test ideas that were pure speculation 50 years ago, have tools and techniques that seemed impossible when the Big Bang theory first emerged. Each decade brings new capabilities, new data, new insights. The James Webb Space Telescope peers deeper into cosmic history than ever before, sees galaxies forming in the universe's first billion years, tests theories about early structure formation, provides constraints on what came before. Not direct observation, but indirect inference. Clues written in the patterns of ancient light. Gravitational wave observatories open another window. Ripples in space-time from the most violent events. Black hole mergers, neutron star collisions, perhaps eventually signals from the Big Bang itself, from cosmic inflation, from whatever preceded our universe's beginning. Those signals would carry information unavailable any other way. Particle accelerators probe the fundamental forces, how they behave at extreme energies, what particles exist and how they interact. These experiments recreate conditions from the early universe. Test theories about what happened in those first moments. Provide pieces of the puzzle about cosmic origins. Each approach contributes. telescopes and detectors and accelerators, theory and observation and experiment, all working together, building a comprehensive picture, answering some questions while revealing new ones. That's how understanding deepens. Yet certain questions might remain forever beyond our reach, not because we're not clever enough, not because technology is insufficient, but because the information doesn't exist to answer them, because the universe itself doesn't preserve the data we'd need. Think about inflation, that brief exponential expansion in the first fraction of a second. It smoothed out the universe, erased details about whatever came before. Like hitting reset on cosmic history, any information about prior states got diluted beyond recovery, spread so thin it became undetectable. Or consider quantum uncertainty. At the smallest scales, reality is fundamentally probabilistic, not just unknown, but unknowable. The precise state of the quantum vacuum fluctuation that might have birthed our universe can't be reconstructed. Even in principle, quantum mechanics forbids it. These aren't temporary limitations, not gaps we'll fill with better technology. They're fundamental features of how reality works. Boundaries written into the laws of physics themselves. Recognition of those boundaries is part of scientific maturity. Understanding what we can't know matters as much as understanding what we can. Does that mean we should stop asking? Abandon the question of what came before? Absolutely not. The boundary between knowable and unknowable isn't fixed. It shifts as our understanding grows. What seemed impossible to answer becomes tractable. What appeared fundamental turns out to be provisional. History teaches humility about declaring limits. Questions that seemed permanently beyond science got answered. The age of Earth, the composition of stars, the mechanism of heredity. Each generation faces mysteries that appear unsolvable. Each generation solves some while discovering new ones. We're in that same position now, with questions about cosmic origins, about what came before the Big Bang. Some aspects we'll figure out. Others might remain mysterious. We won't know which is which until we try. Until we push against the boundaries, test the limits, see what yields and what resists. That process of pushing and testing is valuable regardless of outcome. Even if we never definitively answer what came before the Big Bang, we'll learn something about the nature of time, the structure of space-time, the quantum foundations of reality, about how physics works at the most fundamental level. Those insights will matter, will inform other questions, will deepen our understanding even if they don't fully resolve this one. Science progresses through accumulated partial answers, each insight building on previous ones, creating a structure of understanding that grows more complete over time. And there's value in the asking itself, in wrestling with profound questions, in confronting mysteries that challenge our deepest assumptions. That process shapes how we think, develops our capacity for rigorous reasoning, trains us to distinguish between what we know and what we assume. It also connects us to something larger than ourselves, to the long human tradition of wondering about origins. Every culture has creation stories, explanations for why there's something rather than nothing. Our scientific investigation is the latest chapter in that ancient tradition. What distinguishes modern cosmology isn't that we have better stories, it's that we have ways to test them, to distinguish between possibilities using evidence, to refine our understanding based on observations. That empirical grounding makes all the difference. It means we're not just speculating, not just creating narratives that feel satisfying. We're actually learning about reality, discovering truths that exist independent of our beliefs about them. Truths written in the cosmic microwave background, in the abundance of light elements, in the expansion of space itself. Those truths constrain our theories, rule out ideas that don't match observations, force us to accept conclusions that might seem strange or uncomfortable. That constraint is what makes science powerful, what distinguishes it from other ways of knowing. So when we ask what came before the Big Bang, we're not engaged in idle speculation. We're following evidence, building on established physics, extending theories in ways that make testable predictions. That's legitimate science, even when the answers remain uncertain. The uncertainty itself is honest, a recognition that we're at the frontier, that we're working on hard problems with incomplete information. That humility distinguishes science from dogma. We follow the evidence wherever it leads, change our minds when new data demands it, accept that current understanding is provisional. That provisionality isn't weakness, it's strength. It's how knowledge grows, how we get closer to truth over time, by remaining open to revision, by testing and refining, by building on what works and discarding what doesn't. The question of what came before the Big Bang embodies all of this. The power of science to address profound questions, the importance of empirical testing, the value of theoretical frameworks, the necessity of humility about current understanding, the recognition that some mysteries might be permanent while others will yield to patient investigation. Where does that leave us as individuals, as people wondering about cosmic origins? Not with a simple answer, not with certainty about what came before, but with something perhaps more valuable, an appreciation for the process of discovery, an understanding of how we investigate such questions, a sense of our place in the ongoing human project of understanding reality. We're part of that project whether we're professional physicists or not. Every time we wonder about cosmic origins, we're engaging with these profound questions. Every time we follow new discoveries, we're participating in the collective effort. Every time we think carefully about evidence and inference, we're using the tools that drive progress. That participation matters, not because we'll individually solve these mysteries, but because understanding how we know what we know is valuable. Because scientific literacy enriches our relationship with reality. Because wonder disciplined by evidence is one of humanity's greatest achievements. The Big Bang represents one of those achievements, a triumph of human reasoning and observation. We traced cosmic history back nearly to the beginning, tested our theories against multiple independent lines of evidence, built a comprehensive framework for understanding the universe's evolution. That we can't yet see beyond the Big Bang doesn't diminish that achievement. It highlights how far we've come. A century ago, we didn't know the universe was expanding, didn't know about cosmic microwave background, didn't have the tools to investigate these questions scientifically. Now we do. We have frameworks and observations and tests. We have questions whose answers we're actively pursuing. We have reasons to think progress is possible. That's extraordinary. That's cause for wonder and excitement rather than frustration about what we don't know, because what we don't know defines the frontier. Points toward the next discoveries, motivates the research that will define coming decades. The question of what came before the Big Bang isn't a failure of current science. It's an invitation to future science, a signpost pointing toward deeper understanding. Future generations will look back on our current theories the way we look back on earlier frameworks, as important steps toward truth, as necessary but incomplete, as the foundation for further progress. They'll have insights we can't imagine, tools we haven't invented, data we can't yet collect. But they'll build on what we're doing now, on the theories we're developing, on the observations we're making, on the questions we're asking. That's how science works. Each generation contributing to a project that spans centuries. Building understanding that accumulates over time. We're privileged to be part of that process, to live in an era when these questions can be investigated scientifically, when we have the tools and knowledge to make real progress, when discoveries about cosmic origins happen regularly rather than once in a lifetime. That progress continues. New papers published weekly, new observations analyzed, new theories proposed and tested. The conversation about what came before the Big Bang is active and ongoing. Not settled, but not stagnant. Vibrant with possibility and debate and discovery. And that's where we'll leave things. Not with a definitive answer about what preceded the Big Bang, but with an appreciation for how far we've come in asking the question, for the tools we've developed to investigate it, for the progress we're making and the mysteries that remain. For the profound privilege of living in a time when we can pursue such questions scientifically and make genuine progress toward understanding the deepest nature of reality itself. We've journeyed from the cosmic microwave background to loop quantum gravity, from eternal inflation to the possibility that time itself might be emergent. We've explored theories where universes bounce, where they tunnel from nothing, where they emerge from colliding brains in higher dimensions. Each possibility opens new ways of thinking about what came before, or whether before even makes sense. The honest answer remains what it's been throughout this exploration. We don't fully know, not yet, but that yet carries weight. Because unlike previous generations who could only speculate, we have mathematical frameworks that extend beyond the observable universe. We have predictions we're actively testing. We have multiple approaches converging on similar conclusions, even when they start from different assumptions. Loop quantum cosmology suggests a bounce. String theory points toward higher dimensional origins. Eternal inflation proposes an endless landscape of bubble universes. These aren't wild guesses. They're sophisticated theories built on established physics, making testable predictions about patterns we might detect in cosmic radiation or gravitational waves. What unites these approaches is recognition that the Big Bang probably wasn't an absolute beginning, more likely a transition, a phase change, a moment when our local patch of existence took its current form, but not necessarily when everything began. That shift in perspective matters. It transforms an impossible question into a tractable one. Instead of explaining existence itself, we explain the particular configuration of existence we observe. That's something physics can address, something observations can constrain, something we might actually figure out. The tools keep improving. Telescopes probe deeper into cosmic history. Gravitational wave detectors become more sensitive. Particle accelerators reach higher energies. Each advance narrows the space of possibilities, rules out some theories, strengthens others, moves us closer to understanding. But even as we narrow the possibilities, new questions emerge. If our universe bounced from a previous one, what determined that universe's properties? If we're one bubble in eternal inflation, what governs the inflating field? If time is emergent, what deeper reality does it emerge from? Each answer reveals another layer of mystery beneath. That's not frustrating. That's exactly what progress looks like at the frontier of knowledge. We're not filling in details of a known picture. We're discovering that the picture is larger and stranger than we imagined. Each revelation expands rather than completes our understanding. Consider how far we've come. A century ago, the universe was thought to be eternal and unchanging. Now we know it had a beginning, can describe its evolution in exquisite detail, and are pushing toward understanding what preceded that beginning. That's extraordinary progress by any measure. The cosmic microwave background, discovered by accident, turned out to be a fossil record of the universe at 380,000 years old. Its temperature fluctuations match predictions from inflation theory with remarkable precision. Those same fluctuations might encode signatures from even earlier, from whatever came before our observable universe began. Gravitational waves, predicted by Einstein but only recently detected, open another window into cosmic history. Future observatories might catch ripples from the Big Bang itself, from inflation, perhaps from whatever preceded it. Each detection would constrain theories about origins in ways pure logic never could. The mathematics continues advancing too. Quantum gravity remains incomplete, but multiple approaches show promise. Each offers slightly different answers to what came before. Each makes distinct predictions we're learning to test. The theories are converging even as they're still being developed. What's remarkable is that these questions have become scientific at all. For millennia, humans wondered about cosmic origins through myth and philosophy. Now we investigate them through observation and mathematics. That transition from speculation to science represents one of humanity's greatest intellectual achievements. And it's ongoing. We're in the middle of this investigation, not at its end. The question of what came before the Big Bang is actively being researched. Papers published, observations made, theories refined. The conversation is vibrant and productive even without final answers. That productivity matters more than certainty. Because in pursuing this question, we've learned about the nature of time, the quantum structure of space-time, the behavior of matter at extreme densities. We've developed frameworks that connect the smallest scales to the largest. We've pushed human understanding to its current limits and glimpsed what might lie beyond. Those glimpses suggest reality is stranger than we imagined. Time might not be fundamental. Causality might work differently at the deepest level. Our universe might be one of countless others. These aren't comfortable conclusions, but they emerge from following evidence wherever it leads. That willingness to follow evidence distinguishes science from other ways of knowing. We don't decide what's true based on comfort or tradition. We build theories, test predictions, revise understanding. We accept that current knowledge is provisional, that better observations might overturn today's certainties. The question of what came before the Big Bang embodies that scientific spirit. It pushes against the boundaries of knowledge, tests our theories at their limits, forces us to think carefully about fundamental concepts like time and causality and existence. And it does so through rigorous investigation rather than pure speculation. Future discoveries will reshape how we think about cosmic origins. New telescopes will probe earlier moments. New detectors will find subtler signals. New theories will connect pieces we haven't yet linked. The picture will become clearer even as it reveals new complexities. But whatever we discover, the journey itself has value. In pursuing these questions, we learn not just about the universe, but about how to investigate deep mysteries, about the interplay between theory and observation, about the power of mathematics to describe reality, about the limits of knowledge and how to recognize them. We learn that some questions yield to patient investigation, while others might remain permanently mysterious. That uncertainty isn't failure, but honest recognition of where we stand. That provisional understanding beats comfortable ignorance. That following evidence sometimes leads to uncomfortable conclusions we must accept anyway. These lessons extend beyond cosmology. They're habits of mind applicable anywhere careful thinking matters, ways of distinguishing between what we know and what we assume, between what evidence supports and what we merely hope is true, between legitimate uncertainty and simple ignorance. The question of what came before the Big Bang teaches those lessons at the grandest possible scale, at the boundary between physics and philosophy, where our best theories meet their limits, where evidence becomes sparse and inference uncertain, where we must think most carefully about what conclusions we can legitimately draw, and it connects us to something larger than individual understanding, to the long human tradition of wondering about origins. Every culture has asked these questions in their own way. We ask them through science, through observation and mathematics, rather than myth and tradition. But the impulse is the same, the need to understand where we came from and why we're here. That need is fundamental to human consciousness. We're the species that looks up and wonders, that tries to understand our place in the cosmos, that seeks patterns and explanations. Science is our most powerful tool for satisfying that need, not because it provides comforting answers, but because it provides reliable ones. Answers that match observations, that make testable predictions, that get refined as evidence accumulates. What came before the Big Bang might be answerable, or it might push against the limits of what any investigation can reveal. Either way, the question has driven enormous progress, has shaped how we think about time and existence, has motivated observations that discovered dark energy and mapped the cosmic microwave background and tested general relativity to unprecedented precision. Those discoveries matter regardless of whether they fully answer the original question. They deepen understanding, reveal new phenomena, open new avenues of investigation. That's how science advances, not through linear progress toward predetermined goals, but through exploration of interesting questions that lead unexpected places. And the exploration continues. Every year brings new data, better measurements, refined theories. The space of possibilities narrows. Some options get ruled out. Others gain support. Gradually we move toward truth, even when we can't see the destination clearly. That process requires patience and humility. Patience because progress is slow. Humility because current understanding is incomplete, but also confidence that the process works, that following evidence and testing theories and building on previous discoveries leads somewhere, gets us closer to truth over time, even if we never achieve perfect certainty. The universe operates according to principles we can discover. That's not obvious. Reality could have been incomprehensible, but it's not. It follows mathematical laws we can uncover through observation and reasoning. That comprehensibility is perhaps the deepest mystery of all. Why should the universe be understandable? Why should human minds be capable of grasping cosmic origins? We don't know, but we're grateful, because that comprehensibility makes science possible, makes investigation meaningful, gives us tools to push toward understanding, even when mysteries seem impenetrable. What came before the Big Bang remains mysterious, but it's a productive mystery, one that drives research and sparks insights and connects to testable predictions, one that might yield to investigation or might reveal fundamental limits to knowledge. Either outcome teaches us something important about reality and our ability to understand it. So we continue asking, building theories, making observations, testing predictions, following evidence, remaining humble about current understanding while confident in the process, knowing that some questions take generations to answer, that progress accumulates slowly, that patience and persistence matter more than sudden breakthroughs. The story of what came before isn't finished, won't be finished in our lifetimes, but we're part of it, contributing observations and ideas, building on previous work, setting foundations for future discoveries. That's the scientific project, multi-generational, cumulative, progressively revealing reality's deep structure, and in participating in that project, even as observers following discoveries rather than making them, we connect to something profound, to humanity's endless curiosity about existence, to our capacity for wonder disciplined by evidence, to the long arc of discovery that's brought us from wondering about thunder to investigating cosmic origins. That arc continues. The questions get deeper, the tools more sophisticated, the understanding more complete, but the fundamental human impulse remains constant. We look at the universe and ask why. How did this come to be? What came before? What happens next? Those questions drive us forward, toward knowledge we don't yet possess, toward understanding that remains just beyond our current grasp, toward truth that reveals itself slowly through patient investigation and careful reasoning and honest acknowledgement of what we don't yet know.